Welcome to a screencast on free energy calculations. The objectives of this screencast are to determine how to calculate and interpret the free energy change for reactions that occur with non-standard conditions and to calculate and interpret the equilibrium constant. Now, the delta G naught or delta G superscript 0 values we've been calculating with and looking at so far are standard molar Gibbs free energies. And what this means is that gases involved in the reaction are at 1 atmosphere and aqueous substances are at 1 molar. Now, in general, the reactants and products of a reaction are not under standard conditions. Gases are not always 1 atmosphere. Aqueous substances are not always 1 molar in concentration. And the delta G for a reaction under these non-standard conditions is going to depend upon the composition of the reaction mixture. Now, there's a mathematical relationship that describes this. The relationship is shown here. The delta G of reaction, note that this is not standard. There's no superscript 0. So the delta G for the reaction is equal to the standard delta G for the reaction plus RT ln of Q. And the delta G without the naught is our reaction free energy under whatever conditions, not necessarily standard. The delta G naught, that's our standard reaction free energy. That's what we can calculate from tables for a given reaction. And then the RT ln of Q is the gas constant R times the temperature in Kelvin times the natural log of the reaction quotient Q, and this term has to do with the composition of our reaction mixture. So here's our equation, here's the meaning of the three parts of it, and then Q is the reaction quotient. Remember, that has the same form as an equilibrium constant, but it has concentrations or pressures of whatever the substances are at the given time. And then R, the value that is used here is the 8.314 joules per mole Kelvin value to have agreement with units, so everything is in terms of energies or free energies. Okay, so let's see how to use this with an example of the production of ammonia. Nitrogen plus hydrogen makes NH3, with delta G standard being negative 33.0 kilojoules. Now, we've seen this before. What does this mean? Well, the delta G being a negative number means the reaction is spontaneous, but since it's a delta G naught, it means the reaction is spontaneous under standard conditions. In other words, that all the gases involved, the nitrogen, hydrogen, and ammonia, are 1 atmosphere in pressure. So if we start with 1 atmosphere hydrogen, 1 atmosphere nitrogen, and 1 atmosphere ammonia, then the reaction under those starting conditions is spontaneous. It'll go to form products. That's what spontaneous means. Or we could also say it's a product-favored reaction. So this is something we've done before. This is the standard delta G naught. Now let's consider not standard conditions. So what if we look at the same reaction? And now, instead of starting with 1 atmosphere of each gas, in other words, without trying to only find the delta G under standard conditions, what if we start with 0.1 atmosphere H2, 0.1 atmosphere N2, and 1,000 atmospheres NH3 in our container to begin? Now, if you look at this before calculating and just think a little bit, you'll notice that 1,000 atmospheres of NH3, that's a lot of the right-hand side substance, the product, and 0.1 atmospheres of N2 and H2, that's not very much of the quote-unquote reactants or the left-hand side of the equation substances. So it's not necessarily obvious that the reaction under these starting conditions will be spontaneous, and let's find out. Okay, so here's our reaction equation, or our equation for calculating for this reaction. Delta G of reaction under not standard conditions is delta G naught for the reaction, standard conditions delta G, plus RT ln of Q, and ln for natural log, of course. And Q has the form of the equilibrium constant, but not necessarily with the equilibrium values. So Q for this reaction will be the pressure of NH3 squared times over the pressure of N2 times the pressure of H2 cubed. So let's plug in our values. Delta G naught we were given previously is negative 33.0 kilojoules. R is 8.314 joules per Kelvin. Temperature of, we're going to assume we're at 25 degrees Celsius, so that's 298 Kelvin. Note the Kelvin and per Kelvin will cancel, giving us joules here. And then the natural logarithm of this Q ratio, this reaction quotient, is 1,000 squared over 0.1 times 0.1 cubed. And if we do the math, that term, this sort of composition of reaction term, works out to be about 57,000 joules. Now notice, given the units for the R and the units for the delta G naught, they don't quite agree. They're both energy, but the delta G naught is kilojoules, and this composition term is in joules. So to make them agree, we convert the joules into kilojoules. 57,000 joules is 57 kilojoules. And now, when we add that up, we get that the delta G for reaction under these non-standard starting conditions, these specific non-standard starting conditions, is positive 24.0 kilojoules. Now, that's a positive delta G value. That means the reaction is not spontaneous. But again, make sure that you're careful and understand that the reaction is not spontaneous under the starting conditions of 0.1 atmosphere N2, 0.1 atmosphere H2, and 1,000 atmospheres NH3. And if the reaction is not spontaneous with these starting conditions, then it means that the reaction will go the other direction. It will go to the left to make quote-unquote reactants. And so starting with these given conditions, the reaction will form reactants, use up NH3, make N2 and H2 until it reaches equilibrium. Now, since we know that delta G of reaction equals delta G naught of reaction plus RT log of Q, we can combine this with what we know, which is that at equilibrium, delta G of reaction is 0, and at equilibrium, the reaction quotient Q is equal to the equilibrium constant K. So substituting in 0 for the delta G of reaction and K for the reaction quotient Q, we have that 0 equals delta G naught plus RT ln of K. And solving this for delta G naught of reaction, we get delta G naught equals negative RT ln of K. And note, if we know the equilibrium constant K, then we take the natural log of that, multiply by negative RT, and then that gives us the delta G naught of reaction. So this is an alternative way to get delta G naught of reaction rather than delta G's of formation from tables. Now, of course, the other thing is we might be interested in getting K from delta G naught. So if we divide both sides of this equation by negative RT and then take the natural log of both sides, we get that K equals E to the quantity negative delta G naught of reaction over RT. And so now, if we know the delta G naught, that allows us to find the equilibrium constant K. So we now have a way to link equilibrium and thermodynamics, and that's kind of a cool thing as well. And let's give that a try. With the reaction we've just been looking at, what is the value of the equilibrium constant K sub P for this reaction, and what does it mean? Okay, so let's do this calculation using the equation that we just saw. The equilibrium constant K equals E to the quantity minus delta G naught of reaction over RT. And for this reaction, delta G naught is negative 33 kilojoules. R is 8.314 joules per Kelvin, and temperature is 298 Kelvin. Do note, this is a negative of the quantity inside here, and the delta G itself is negative, so that's a negative negative, so this whole quantity will be positive. Also note that the Kelvin cancel but we have kilojoules in the numerator, joules in the denominator, so we have to make those agree. So let's convert the kilojoules to joules. Now the joules will cancel, and e to the this whole quantity gives us about 6.1 times 10 to the minus fifth. Do note in this exponent here, it depends upon round off quite significantly, and so this number in front of the at the beginning of the case of SP value is going to be highly dependent upon how you do the round off, and usually it's not really legitimately accurate to more than 2 sig figs, if at that. So I've rounded off to 2 sig figs here. And now what does this mean? Well, this is a very big K value, so the reaction we say is product favored. And then again, remember that what product favored means is that when we reach equilibrium, we have more quote-unquote products, the substances written on the right side of the equation, than reactants, quote-unquote, the substances on the left side of the equation. And that is it for free energy calculations.